going to be looking at the region between curves in this section. Now when we talk about the region between curves, a curve sketch is always very helpful to get us started. Now a couple things about regions between curves. Let's go ahead and look at a couple different types of graphs. Let's say we have a curve like this and another one like this. So the region that we were trying to find in this particular example would be this bounded region here. Now we can do this two different ways. We can find our curve using this idea of a rectangle. That's how I always start these. And you always would take upper minus your lower curve. So let's go ahead and call this f of x on top, g of x on the bottom. Now notice from this region, let's say a to b, where these intersect each other, f of x is the upper curve. But if we switch regions, let's say to over here, g of x is the upper curve. So you have to be careful about which curve is where. So for this particular example, the area would be the integral from a to b, these points of intersection, of your upper curve, f of x minus g of x, the lower curve. And then the width of this rectangle is on the x-axis, so this is called dx. Okay, so this is one way that we could find the region between curves. You always take your upper curve minus your lower curve when we're using a vertical rectangle that cuts the x-axis. Now if we looked at this same graph another way, I guess it doesn't have to be the identical graph, but one similar, you can see, actually I don't want to have one drop below the x-axis yet. You can see for this region, I could split this up another way. So this is still the same region I'm looking for, but I could also use horizontal rectangles, but it's not as easy in this particular case. I always extend my rectangles out to touch the axis that I'm going to be using, so this would be dy. So in this particular case, these points of intersection, I'm not interested in the x values, I'd be interested in the y values. So we'll call this C. Let's say this would be D, and then we have a lot more going on here than we think. So here, when I find that area, I actually have two regions. I have this region where my right-hand curve, we'll call this h of x, and then we'll call this parabola that's opening down, let's call that u of x. So we have two regions here, and they're split right here. So this is not a rectangle, this is delineating the two regions. So this region on top I'm going to call region 1. In this region 1, if you'll notice, the right curve and the left curve are the same. So when I talk about right minus left in this particular case for my dy, I have to figure out what's going on here. I have to split this curve up. So this would be a curve, let's say y equal negative x squared, and it's got some other things going on here. You can see that this is a bad choice, because if I talk about region 1, the right and the left curves are different parts of the same curve. Now down here for region 2, I would have h of x for my right-hand curve, and then u of x for my left-hand curve. So this would be h of x, this would be u of x. Now I would have to rewrite these in terms of y. So I'm using dy's here for this particular case. So I'm going to rewrite this as h of y and then u of y. So I'd have to take my h of x and u of x and rewrite them in terms of y. So I'm going to call this area of region 2. So I would integrate this from these points of intersection. So this would go from C to D, and it would be right minus left. So this would be h of y minus u of y dy. Because I have a horizontal rectangle, and you'll notice when I extend these touch the y-axis, and so that's why that idea of dy comes into play. So that's area of region 2. Area of region 1, I'd have to know more about the curve to figure out exactly what's going on here. I'd have to split this for the right minus left so I could set up that integral. So you can see a lot of times there's a really obvious choice. For instance, the same curve, dx's are much better than dy's. So here I'd have plus area of region 1, whatever that would turn out to be. And again, I have trouble setting it up because of this u of x, which I'd have to rewrite as u of y dy. And my limits of integration are even tough because I'd have to go from D and then I'd have to find this maximum point. So again, fraught with problems. Make sure you look at the picture first, see if you can have a single region versus two regions, and I think that curve sketch is helpful, although not always necessary. So let's go ahead and start looking at some examples. Some of these examples we will be just setting up, and some of them we'll actually be solving. So for this one, let's go ahead and find the area bound by, let's use two functions here. Let's use y equal x squared minus 7 and y equals 6x. Now a curve sketch is not always necessary, but helpful, and in this case that is the same as well. So we need to figure out what this picture looks like. Well, this is a parabola that's opening up, and this is a line with a positive slope. So let's go ahead and set these up. So the line of positive slope, y-intercept is 0, and then my slope is pretty steep. It's going to rise 6, run 1, so I'm just going to sketch it through right here. So this is y equals 6x. Okay, now let's go ahead and look at our other piece here, y equal x squared minus 7. This is a parabola that opens up, and it goes down 7 units on my y-axis. That's just a transformation of a graph. So it comes down here 7 units, and then it opens up. Now, one thing I need to figure out are what are these important points right here. Now, if you notice as we're setting these up, if I switch to my right minus left curves, I have two regions. I'd have region 1 where I have the same curve right and left, and then I'd have a region 2. So I think definitely on this particular case I want to have these vertical rectangles, so I'm using dx's. So I need to figure out where these points are. So I need to find points of intersection, and in order to find points of intersection I set the equations equal to each other because they're both solved for y. So I have x squared minus 7 equals 6x. I'd subtract the 6x over, factor, set equal to 0 using the 0 factor property, and I'd have x equal 7, x equal negative 1. So this would be the point negative 1, this would be the point 7. Okay, so there's my points of intersection. So what this is telling me that these rectangles are going to start over here, and they're going to continue to sum up. Remember that idea of Riemann sums. And they're going to go from negative 1 to 7 on the x-axis. So I know my integral will go from negative 1 to 7. Now, we always take the upper minus the lower. The upper curve is pretty easy to see here. The upper curve is always the same. So that's 6x minus my lower curve. Make sure you have parentheses here because the negative sign has to distribute. Couple things. Remember, if we had used horizontal rectangles, I would have had to solve this for x equals stuff in terms of y, and same with this one. And not only that, but I have to be very, very careful about when I rewrite this that I have the two regions. So dx is here, vertical rectangles are a great idea. So rewriting this, I have the integral from negative 1 to 7, 6x minus x squared plus 7 dx. So this is my integral that I'm trying to solve to find the area bounded by the regions. So let's go ahead and solve it from here. We won't be solving all of these because they take so long. We'll just be focusing on the setup for most of them. The integral would be 6x squared over 2 minus x cubed over 3 plus 7x, which simplifies to 3x squared minus x cubed over 3 plus 7x, and I evaluate from negative 1 to 7. Plugging in the 7 first, 3 times 7 squared, 7 cubed over 3 plus 7 times 7. Now when you do your upper minus your lower, make sure you put your brackets up for the lower. So I'd have 3 times a negative 1 squared minus negative 1 cubed over 3 plus 7 times negative 1. Okay, so there's quite a bit going on here with some of these. So this would be 3 times 49 minus, and then 7 cubed is 343 over 3. And I'm going to go ahead and distribute the negative. Negative 1 times negative 1 is 1. 1 times 3 is 3. And when I distribute the negative, it becomes a negative 3. This would be a negative 1/3 minus a negative 1/3 is a positive. The negative sign out front would switch it back to a negative. And then my last one here would be a negative 7. Distribute the negative, it becomes a plus 7. Okay, so 120 plus 27 would be 147. The 343 over 3 doesn't reduce. Actually, I'm going to reorder these a little bit. I'm going to put all my integer values over here and then my fractions on the end. So 147 plus 49 minus 3 plus 7, 10. So that equals 200 minus, and this would be negative 343 minus 3 would be a negative minus 1/3 would be a minus negative 344 over 3. Finding a common denominator, 600 minus 344 over 3, and then we'd have 256 over 3. That's my area bounded by this region. We leave everything as improper fractions. We do not convert these to a mixed number. So big takeaways here. Vertical rectangles in this particular case are easier because I have the same upper curve over the entire interval. Okay, and if I had used horizontal rectangles, I would have had 2 regions and I would have had to switch that out. So a nice little curve sketch is always very, very helpful. Although it's not necessary, I still have to be able to find some way to find my upper and my lower curve though. So curve sketching talents are important on these. Some of my favorite ones are trig functions. With the trig functions and finding points of intersections, you get to practice solving your trigonometric equations. So let's go ahead and find the area of the region bounded by, and let's do two trig functions. Let's do y equal secant squared of x all over 2 and y equal cosines. Let's do 2 cosines squared of x. A couple quick things when you're writing up your handwritten homework problems. It's very important to me that you put parentheses around the arguments of your trig functions because it clarifies what the argument is in case you have other functions running around and other constants. So please always put parentheses around the arguments of your trig functions. So we need to figure out a couple things here. We need to know what the graph looks like. We need to either know upper, lower, right, or left, and we need to know points of intersection. So I'm going to start with points of intersection. That's going to give me a little bit of information about the curve sketch perhaps. So the way I find points of intersection are you set the two equal to each other because they're both solved for y equal. So I have secant squared of x over 2 equals 2 cosine squared of x. I'm going to put that over 1. So if I cross multiply, that would be one way I could kind of get started here, but instead I'm going to rewrite everything in terms of sines and cosines. So secant squared is 1 over cosine, so this is 2 over cosine squared of x equals 2 cosine squared of x over 1. So now when I cross multiply, I get 4 cosine to the 4th of x equal 1, divide both sides through by 4, and then I'll take the 4th root of each side. So that would have cosine of x, 1 to the 1/4 would just be 1, and then 4 to the 1/4, this is the 4th root of 4. That means to take the square root twice. So the square root of 4 is 2, and the square root of 2 is the square root of 2. So this is plus or minus root 2. Now this doesn't look as familiar in this form. Let's look at this as the cosine of x equal plus or minus the square root of 2 over 2. Okay, so when we're trying to solve here, what we're coming up with is this point of intersection. I could take the inverse cosine of each side, and again, you're not going to have calculators, so it's very important that you recognize these values from your unit circle. This would give me x equals positive or negative pi over 4. Okay, so what we're looking at here are values saying the cosine of what number or what angle is positive square root of 2 over 2. That's positive pi over 4. And cosine of what angle is negative square root of 2 over 2 is negative pi over 4. So again, knowing your unit circle is going to be important here. So I know that they intersect at x equal pi over 4 and negative pi over 4. So let's go ahead and try and recreate our graph here. Now the basic graphs are really important to know, like sine and cosine. The other ones we can usually come up with if we need to. So let's go ahead and start off with cosine squared. Easy values are going to be 0, of course. So cosine of 0 is 1, 1 squared is 1, 1 times 2 is 2. So let's go ahead and put this up at 2. Okay, now we also know something's going on at pi over 4. So let's make sure we have a pi over 4 here and a pi over 2. And then a negative pi over 4 and a negative pi over 2. So these are just some points I want to try. So if I plug pi over 4 into this graph, the cosine of pi over 4 is square root of 2 over 2. So I'm going to change my notation here a little bit. F of pi over 4 equals 2 cosine pi over 4 quantity squared. And I'm only squaring the cosine. So that would be square root of 2 over 2 quantity squared. Root 2 times root 2 is 2. 2 squared is 4. This is 1. So at pi over 4, it looks like to me I'm at a height of 1. And of course the same will happen over here because I'm at I'm squaring. So when I square a positive or a negative, I get the same value there. Okay, pi over 2, the cosine of pi over 2 is going to be 0. 0 squared is 0, 0 times 0 is 0. So here I am. Now this looks like it could be a sharp V, but we know it's a trig function, so it's this nice smooth curve. And our graph really that we're only interested in really only goes to pi over 4, but I'm going to sketch in a little extra here. And since we know that the cosine squared times 2 will never fall below the axis because I'm squaring, so I'll get all positive numbers, this is periodic. So this is kind of an idea of what this picture looks like. Curve sketch, not an exact picture. I'll turn back up. Okay, so now let's go ahead and look at our other graph. Y equal secant squared of x over 2. So again, this would be the same as 1 over cosine squared. Okay, so we'd plug a 0 in. Cosine of 0, we plug a 0 into here. Cosine of 0 is 1. 1 squared is 1. 1 times 2 is 2. But that's a 2 in the denominator. So if we're talking about a 2 in the denominator, that would be 1 over 2 or a half. So I know that my graph is going to start here for my secant squared. Now the secant squared will build off and open up kind of like a horseshoe. I do have points where this is undefined, particularly at pi over 2. I'll have a vertical asymptote, but again we're only interested to pi over 4. So let's see what's going on at pi over 4. So let's look at f of pi over 4. Okay, so this would be 2 cosine squared. This looks very familiar right here. So that would be square root of 2 over 2 squared. So it looks like I'm hitting right here again because I got a 1 here, so 1 over 1 is 1. So this shows me that it's opening up. So this region that we have here is going to be the region that I'm trying to find the area of. Now, as we did in our last problem, I have to decide between horizontal and vertical rectangles. If I used vertical rectangles, you can see in this region my right and left curves would be the same function, and then over here my right and left curves would be the same function, although a different function. So I'd have two regions that I needed to work with. And if I use horizontal rectangles, I don't want two regions, plus I'd have to have a dy, and everything is solved for in terms of dx anyway. So I'm going to use vertical rectangles. So when I start to set up my integral, I know I'm going to go from negative pi over 4 to positive pi over 4, because I'm on the x-axis and that's where my points of intersection are. And then I need to do my upper curve minus my lower curve. Well, my upper curve was 2 cosine squared of x, and then my lower curve was secant squared of x over 2 dx. So there's my setup. Now, once we get our setup, we can go ahead and integrate, but this is the kind of the thing we need to focus on, because the rest of this should be pretty straightforward, looking at integrals or even antiderivatives. Think antiderivatives. Remember, those two terms are interchangeable. So this is the idea of the upper minus the lower, and I always extend these to touch the axis, so I realize that I'm using dx's, and if I use dx's, my original functions have to be in terms of x as well. So this one will solve, just because this kind of has an interesting little way to solve for the cosine squared of 2x. We're going to use a half angle formula here, and this is a good one to have on your note card for the exam. Might come in handy. So for this half angle formula, because we can't integrate cosine squared of x, we have no way to do that. So we can use this half angle formula, cosine squared of x equals 1 plus cosine of 2x all over 2. Now there's another half angle formula that often comes in handy. We're going to use this one right now for this problem, but there's another one that's sine squared of x equals 1 minus the cosine of 2x over 2. Now the reason we like these formulas is it allows me to rewrite things so I can integrate them, because right now I have no way of integrating cosine squared of x without rewriting it somehow. So these are two good formulas. We're going to use the red one today. So first one, I'm going to split this up into two integrals. My first one will go from negative pi over 4 to 4 to pi over 4, and this is going to be 2 cosine squared of x would be 1 plus the cosine of 2x all over 2 dx. Okay, and then my second integral would be negative pi over 4 to positive pi over 4. And actually it's a minus, so if I wanted to, I could have that minus out front as well. Or I could put it inside the integral, either one. And this would be, I'm going to pull out the half as well, secant squared of x over 2, which I pulled out front, dx. Okay, I'm going to change that to a different color to help me keep track. Okay, so for this first one, you can see that the 2's cancel. So I can cancel the 2's. And I'm just left with the integral from negative pi over 4 to positive pi over 4 of 1 plus the cosine of 2x dx. Okay, and then for my other one, this one's actually easier. Minus 1/2. This is an antiderivative. The derivative of tangent is secant squared. Therefore, the integral of secant squared is tangent. And this is from negative pi over 4 to positive pi over 4. In fact, let's take this one and evaluate it right now. So this would be the tangent of pi over 4 minus the tangent of a negative pi over 4. Drag along that negative 1/2. Tangent of pi over 4 is 1 minus tangent of negative pi over 4 is negative 1. So 1 minus a negative 1 would be 1 plus 1 is 2. Half of 2 is 1, but it's a negative, so I get a negative 1 here. So that's one of my parts of the integral here. So it's not my answer, it's just one of the parts I need to remember to keep track of. Okay, next one. The integral of 1 is x. The integral of the cosine of 2x, I have to use a u substitution. U is 2x, du is 2 dx, so I need to multiply by a 2 on the inside, compensate with the 1/2 on the outside. So I already integrated the 1. And so we can see here that this just turns out to be cosine of u du. So again, I have that x half. The integral of the cosine is sine of u, but u is equal to 2x in this case. And now I can evaluate this from negative pi over 4 to positive pi over 4. So plugging in my upper first, I have pi over 4 plus 1/2 sine of 2, because there's a 2 in here, 2 pi over 4. That's my upper. Minus my lower, negative pi over 4 plus 1/2 sine of a negative 2 pi over 4. So pi over 4 plus 1/2. Now 2 pi over 4 reduces to a half. The sine of pi over 2, or the sine of half pi, is 1. Minus a negative is the same as a positive. And then over here I have minus 1/2 because I'm going to take the negative and distribute it. The sine of negative pi over 2 is negative 1. So here I have pi over 4 plus pi over 4 is 2 pi over 4. And then half plus a half is 1. So 2 pi over 4 reduces to pi over 2 plus 1. Now don't forget, I also have this one up top. So I need to bring this down for my minus 1. And they cancel, and I'm just left with pi over 2 for that total area. So pi over 2 is the correct solution there. This is the exact area of this shaded region. Would be pi over 2. It's kind of interesting. Now we want that in exact form. We don't want that as a decimal approximation, so it's best to leave it in exact form. That's fun. I like doing this. It has like everything. It's got a little algebra, it's got solving trig equations, curve sketching, some trig identities and half angle formulas, lots of fun integrals too. So that's a really good problem. Let's go ahead and look at our next one. So the focus on these problems isn't going to be necessarily the integration part that we're going to be covering. You can definitely be doing those in your homework and your handwritten homework, and also on your exams. So I want to focus on the setup because that's what takes the most time, is the integration, whereas the setup takes a little bit less time. So I want to be able to show up and set up a lot of these on each problem, whether it's on your test or your handwritten homework. So setup is very, very important. So for our next one, we still want to find the region bounded by, or find the area bounded by. Let's go ahead and use y equal another trig function. I like trig functions. Always put parentheses around the arguments of your trig function. And let's do another 5. Let's do 2x here. And let's go ahead and focus on this from 0 to pi. So 0 to pi is kind of our thing that we want to be looking at and focusing on here. So we need to come up with curve sketch for this, but in order to do that we need to find points of intersection. So let's look at points of intersection. So to find points of intersection, you both set them equal to each other. And we're going to use another trig identity here, and this is another good one for your note cards. This one's called a double angle identity. And you never know what trig functions you're going to rewrite, or an identity that we'll need to rewrite. So a lot of times you just have to search out these identities. Now if we had a physical textbook, we could usually find those in the front or the back cover. They always have the trig identities written there. But since you have an ebook, you'd have to look in the cover of your ebook at the formulas given. So the one that we're going to use here is the sine of 2x equals 2 sine of x cosine of x. Now one of the reasons I want to make sure that I see these in the lectures is so you have a chance to recognize the more commonly used ones. So that way you can have them in your notes. So I don't expect you to know these, and I'll show them to you during our lectures as we're working. So 5 sine of x is equal to 5 times 2 sine of x cosine of x. I guess I said I don't expect you to know these. I don't expect you to know these right now, but on a test you definitely will want to know these. So we'll get these set equal to 0 by subtracting. Okay, and then when I look at these and I subtract them, and they're set equal to 0, I should be able to factor. So I'm going to factor out a 5 sine of x. And if I factor that out, I'm left with 1 minus 2 cosine of x equals 0. 5 sine of x equals 0. These are fun. Okay, and then my other one is 1 minus 2 cosine of x equals 0. So here this is, I can divide through by 5 and I get sine of x equals 0. And this is saying, where is the sine of x equals 0? Well, remember, we're limiting ourselves from 0 to pi. So this is true at x equals 0 and at x equal pi. Here I have cosine of x. I would subtract the 1, divide through by -2, and I get a half. Where does the cosine of x equal a half? Between 0 and pi. And that would be at x equal pi over 3. So these are my 3 points of intersection. Okay, so I'm going to put these in order. 0, pi over 3, and pi. So these are my points of intersection. So now as I start to try and graph this, I kind of have an idea of what these curves look like anyway. You know, the standard sine curve, and it looks like with the sine of 2x I need to change the period and expand it. But I have to focus in on 0, pi over 3, and pi is where they cross. Okay, so let's go ahead and do our curve sketch. And if you're wondering if you would need to be able to create a curve sketch like this on a test, definitely. You should be able to logic your way through a quick curve sketch. So let's go ahead and start with 0. Now remember our two functions. We'll do one in blue. Let's do y equal 5 sine of x in blue. So if we plug a 0 in here, I get a 0 back out. The sine of 0 is 0. Now I want to see what's going on at pi over 3, and then again at pi. So I'm going to come out here to pi. And here would be pi over 2. And then pi over 3 would be right about here. Okay, so let's see what's going on at pi. The sine of pi is 0. 0 times 5 is 0. The sine of pi over 2 is 1. 1 times 5 is 5. So this would be this maximum point right here at 5, we'll say. Okay, so there's kind of a start to what we have going on here with the sine of x. So if we sketch this in, it's going to be a nice smooth curve. And this is y equal 5 sine of x. Well, I will write it on in a second. I don't want to write over where the other curve might be coming in. So our next curve is y equal 5 sine of 2x. So same thing, we want to go ahead and plot our points. If we plug a 0 in here, we get a 0 back out, because we already know these are points of intersection, so they have to match at these 3 points. And at pi, sine of 2 pi is 0. 0 times 5 is 0. And then at pi over 3, I also know that I'm going to cross. So we're going to call that right about there. So whatever that number is, I don't know what it is, but we can figure that out. What I do need to find out is whether my orange curve, 5 sine 2x, is above or below here. So let's go ahead and pick a point, let's say like, let's do pi over 4. So pi over 4 would be halfway here. So if I do the sine of pi over 4, 2 pi over 4 is the same as pi over 2. The sine of pi over 2 is 1. 1 times 5 is 5. So at this point, this graph is clear up here. So it's going to come in and it's going to maximize out here and then turn back down. And let's see what's going on at pi over 2. It's going to cross. 2 pi over 2 is pi. Sine of pi is 0. 0 times 5 is 0. So it's going to come up here and cross, and then it has to come back up. So this is a general curve sketch here. Whoops, I missed it. Let's try that again. And it's going to come down here, and it has to turn back around. Now if I want to know what's going on here, I could choose something like 3 pi over 4. And 3 pi over 4 would be -5 if you want to plug that in to check it. So I have two regions here. I have region 1 and region 2. So region 1 and region 2. Now if you notice for both of these regions, everything is solved for x already. So I want to keep everything in terms of x if I can. So I'm going to go ahead and set up the integral for region 1. So region 1 plus region 2. So I can see that these vertical rectangles will go from 0 to pi over 3, which is our point of intersection. So 0 to pi over 3. Then I have to take my upper curve minus my lower curve. Well, my upper curve is the orange. That's 5 sine 2x. Minus my lower curve, which is 5 sine of x. And the incremental width of that rectangle is dx. Now I need my second region. My second region will go from pi over 3 to pi. Now the reason I need a second region is the upper switched from the orange to the blue curve, so I need to have a new region. So this would be pi over 3 to pi, and then my upper curve is 5 sine of x minus 5 sine of 2x dx. The orange curve is my lower curve now. So again, I have two regions here, 0 to pi over 3, my upper minus my lower, and then the upper and lower switch from pi over 3 to pi. Now, I'm not going to spend the time solving this because you should be able to integrate these pretty straightforward. There's no tricks to this one. But when I integrated this, I had 25 halves as a solution, so if you want to double check to see if you can match that answer, that would be great. So a curve sketch here is important. Knowing your unit circle, very, very important. So make sure you either have that memorized or have it very readily available to you on your note card for an exam. Now, something we haven't worked very much with are absolute values. So I want to make sure that when you come across one of the absolute value problems that you know what to do. So we'll go ahead and set this one up. Again, I'll leave the integration to you. We want to find the area, bound by, let's do y equal absolute value of x minus 12 and y equal x over 2. So the nice thing to do first is a quick curve sketch, and then we can figure out points of intersection here in a minute. And the reason I want to do my curve sketch first on this one is we'll be able to visualize a lot more of what's going on and where they intersect. So quick curve sketch. This is a sharp V, and it's going to go 12 units to the right. That's one of the characteristics of transformations that we work with. So let's go ahead and focus in on 12 units to the right. We'll kind of look at the first quadrant. So I'm going to say that this is 12 units. So if I plug in a 12, 12 minus 12 is 0. Okay, and then from here I know it's a sharp V. And it's symmetric on either side. That's kind of bowed a little bit. There, that's better. So this is my y equal absolute value of x minus 12. Now this line, y equal x over 2, this has a slope of a 1/2 x plus 0, so it's telling me I go through the origin for my y-intercept, and the slope is 1/2. That's a positive 1/2, and so I know this is a positive sloping line. And I'm just going to sketch it in some positive sloping line. So this is the region that I'm bound right here, that I'm trying to find the area of right here. So it looks like to me I definitely would like to use vertical rectangles again, because if I use horizontal rectangles I'd have to solve this for x in terms of y. I don't want to do that. So I'm going to use vertical rectangles. I'm going to have two regions though. So here's region 1, and then here's region 2. Because I have to split these because the bottom part of this graph it's still the same absolute value function, but it's a different piece of the absolute value function, because this left-hand side has a negative sloping line and the right-hand side has a positive sloping line. So that's where it gets a little bit dicey. So let's go ahead and write out what this means. So we have y equal the absolute value of x minus 12. Well, I have two things going on here. I have the negative part of x minus 12 and I have the positive part of x minus 12. So this is negative x plus 12, and this is equal to just x minus 12. And these are for the values of x that are less than 12. These are the values of x that are greater than 12. Now the equal to could go on either spot here. It doesn't really matter. because when I plug 12 in, I get the same thing back. So usually only have them on one though to avoid confusion. So on the left hand side, I want to figure out what this point of intersection is. And on the right hand side, I need to figure out what the point of intersection is as well. I know the middle one is 12. So on the left hand side, this would be y equal negative x plus 12. And on the right hand side, this would be y equal x minus 12. Okay, so let's look at our points of intersection. I'm going to take negative x plus 12 and set it equal to x over 2. So if I subtract the x over 2, or if you want to add the x across, that's fine as well. I get 3x over 2 equals 12. And solving for x, I'd multiply both sides through by 2/3, and I would get 8. So this point is 8. In my other point of intersection, I would take x minus 12 equal x over 2. So I'd get x over 2 equal 12 when I subtract the x over 2, and I get x equal 24. So I'm setting up two regions here. So my region 1, I would integrate from 8 to 12. Now my upper curve is the line, not the absolute value function, but just the line, so it would be x over 2 minus the lower curve here is the absolute value function, so I'm going to subtract, make sure you have parentheses, otherwise the negative sign won't get distributed, and there's my negative minus the quantity negative x plus 12. Okay, now my second region goes from 12 to 24. Again, this is region 2. My upper curve is still the x over 2, but the lower curve is now the positive sloping component of the absolute value function, so that would be minus the quantity x minus 12 dx. So that would be what my setup looks like. And of course, you can simplify these quite a bit. So this would be the integral from 8 to 12. X over 2 plus x would be 3x over 2 minus 12 dx. 12 to 24, x over 2 minus 1 over minus 1x would be a negative x over 2. Fix that up. Plus 12 dx. Don't drop your dx's. Now if you go through and solve for this, it's 48. These aren't too bad to work with once you get going. But I want to focus on the part where we're integrating. So it's really important that we get that correct integral set up and get the correct points of intersections. Now the next one we're going to look at, we keep talking about horizontal and vertical rectangles, but we've only used vertical so far. Next one we'll see that horizontal or vertical could work, but one is definitely easier than the other. So let's go ahead and find the area. Bound by, let's use y equal 2 minus x over 3. And this one's going to be a little bit different. X equal, we're used to y equal, x equal 3y squared. So before we really get started too much here, let's think about what these look like. This is a line, minus 1/3 x plus 2, with a y-intercept of 2 and a slope of a negative 1/3. So this is a negative sloping line of some sort. Now this one, this is interesting. This is a parabola opening on its side. So if we wanted to, we could look at this as y squared equals 1/3 x. That might be a little bit easier to look at. And if we do that, we can see that it's a parabola opening on its side to the right because it's a positive. Y squared equals a positive x. So that's our curve sketch. We need to see what this is going to look like when they intersect. We already kind of have a pretty good idea just from these two basic ideas. It's probably going to look something like this. But we need to plot some points to figure it out for sure. Okay. I think the easier thing to start with here would be some points of intersection perhaps. So if we think about points of intersection, we can't set these equal to each other the way they're written. And the reason we can't is this one is x equal, this one is y squared equal, this one is y equal. So this is going to be difficult to solve for y because I'll get two roots, a positive and a negative. So let's go ahead and solve this one for x. If we solve this for x, I end up with x equals 6 minus 3y. And the easy way to do that is to multiply through by 3 and then solve for x. So I have x equals 6 minus 3y and x equals 3y squared. And then let's go ahead and find our points of intersection. 6 minus 3y equals 3y squared. Subtract everything across. 3y squared plus 3y minus 6 equals 0. Divide through by 3. Factor, use that zero factor property. And I get y equal negative 2, y equal 1. So these are going to cross at y equal negative 2, not x equal, but y equal negative 2, and at y equal 1. I'm going to spread this out a little bit more. So here's negative 2 and 1. Okay, so I already have an idea what this graph looks like. So that's pretty helpful. I know it's a parabola opening on its side. So let's go ahead and try and plot some points with that. I'm thinking that if we plug a 0 in, we get a 0 back out. So that's helpful. And it's opening to the right, so I think it's going to look like this. But let's go ahead and plug in a y equal 1. If we plug in y equal 1, 1 squared is 1, 1 times 3 is 3, I get x equal 3. So this would be the point 3, 1. And I could also do the same if I was trying to figure out my other value over here. If I look at plugging in a 1 for y, I wonder what would happen if I plugged in a negative 1, and you can see I'd get a 3 back as well. So this is the ordered pair 3, negative 1. It's kind of a little wobbly there, but there's my parabola opening to the right. Now for this other one, I kind of want to stick with this form just because that's easier to graph. So this is a y-intercept of 2. Okay, so that's going to come up here 2 units. And then the slope is a negative 1/3. And I know that my points of intersection are at y equal 1, so that's got to be this point. And then my other intersection is at y equal negative 2. I'm going to resketch this. And the reason I'm going to resketch this is it has to hit somewhere over here, so I have to make it a little bit more steep. There. So here's y equal negative 2, and here's y equal 1. So this is going to cross this line, and that of course threw off this scale. So this line is going to come in here and cross here and here. So my value of 2 is actually right up here. So you can see that if I split this into, if I use dx, which I can, I'd have 2 regions. They'd split right here. If I use a dy though, I can use the same right curve for everything. So dy is preferable. dy is easier. So that means everything has to be in terms of y. Well, I already know my limits of integration are from negative 2 to 1. My right curve is going to be 3y squared. And then my left curve is, my right curve is going to be 6 minus 3y because it's the line. And then my left curve is this x equals 3y squared. So this is the easier one for me to set up just because it has the same right and left curve over the entire region. Now if you want to go ahead and integrate this, you'll get 27 halves. Now dx is a little harder. And this is 3y squared over here. But I can set it up. I'm going to have 2 regions. So for dx's, trying to look at this. So for my dx's, my 2 regions split right here. So here's region below, here's region above. Now the reason they split is if I solve for x equal 3y squared, I get y squared equal x over 3. I get y equal plus or minus the square root of x over 3. So the curve above this would be the plus square root of x over 3, and the curve below would be the minus square root of x over 3. So when I set this up for my top region, I'll call this region 1. My limits of integration will go from 0 up to 1, so I go from 0 to 1, and then my right curve is this line 2 minus x over 3. But again, these are in terms of dy, so I need to make sure I have this set up correctly. Okay, so I think I had this set up wrong. So the dx is harder, so we're going to take these and I'm going to split this right here for my dx. Okay, and I have vertical rectangles for my dx. It's kind of getting a little ugly here to see what's going on. So here's my dx's. So I'll call this region 1 and region 2. Okay, so when I talk about region 1, this is going to go from 0 to this point of intersection. Now if you remember, this point of intersection was where y is 1. So where y is 1, I can plug back in and figure out what x is. If y is 1, 1 squared is 1, 1 times 3 is 3. This is the ordered pair 3, 1, which I see right here as well. So this is going to go from 0 to 3. So I have my integral from 0 to 3, and then my upper curve is going to be the positive part of this. This would be the square root of x over 3 minus the lower part was the negative square root of x over 3 dx. Plus region 2. So region 2 is going to go from 3 to whatever this point is down here. So this point down here I think we found earlier as well with our points of intersection. This is where y was negative 2. If we plug a negative 2 back in here, I get 4 times 3 is 12. So this is going to go from 3 to 12. So then I need my upper and my lower. My upper curve would be the line, and so that's 2 minus x over 3. Now if you notice, everything here is in terms of x, and my other one, everything had to be in terms of y. So I have my 2 minus x over 3, and then my lower curve is the negative, because it's falling below, root x over 3 dx. And of course this would simplify. This would be the integral from 0 to 3 of root x over 3 plus root x over 3 is 2 of these roots x over 3 dx's. And this would be plus the integral from 3 to 12 of 2 minus x over 3 plus root x over 3. Minus a negative is the same as a positive. Now if you did this and integrated it, you'd get 27/2. Same answer either way. Doesn't matter which method you choose. If you don't make any mistakes, you'll get the same solution. But to me, the dy is way easier. And my picture got a little bit ugly here, but make sure you sketch in your rectangles so you make sure that you don't make any mistakes when you're setting up your integral. Now, a lot of the things we're coming up with right now will really serve us well when we're trying to find volumes of rotated figures. So this curve sketch idea is going to be very important, not only in this section, but some upcoming sections as well. Let's go ahead and look at this one. Again, we're just setting up region bounded by. In this case, instead of an upper and a lower function, I'm just going to have a horizontal line, y equal 1 and y equal x to the 2/7. Okay, so y equal 1, that's easy enough. If we want to set these up to find my points of intersection, that's pretty straightforward as well. So I get x to the 2/7 equals 1, x is equal to 1. If you want to solve, you'd raise both sides to the 7/2. Setting these up is going to be pretty straightforward. Now, when we're looking at this, you can say there's only one point of intersection. That's kind of strange. We'll see what happens here. Y equal 1, that's easy. It's just a horizontal line. So there's y equal 1. Now let's go ahead and look at y equal x to the 2/7. If we plot some points here, if I plug a 0 in for x, I get a 0 back out. If I plug a 1 in for x, I get a 1 back out. So there's that point of intersection of 1, 1. Now this area isn't bounded touching down here. This area that we're looking at in this particular case is in here. So I have a couple of options. I think I could set this up two ways. Let's go ahead and look at this in terms of vertical rectangles first. So again, this was the ordered pair 1, 1. And you can see that it's bound over here. If we plug in negative value here, I guess I could go in the negative direction, but when I square it, it becomes positive. So I need to make sure I'm also bound by, in this particular case, x equals 0. So this is the line x equals 0, just to make sure we're bound an entire region. So let's go ahead and look at dx's. So here would be my dx. So I can see that this integral is going to run from 0 to 1. And my upper curve is 1. It's just 1. It's not y equal 1, it's just 1. It's a height of 1. And I subtract out my lower, which would be x to the 2/7 dx. Now if you want to integrate this, you'd get 2/9. So if you want to check that, you can. Now my other option here is to use a dy. dy would still go from 0 to 1, but on the horizontal, not on the horizontal, but on the vertical. So it's going in this direction. And here I would use my right minus my left curve. Now my right curve is this x to the 2/7, but I can't use an x to the 2/7 here because this has to be in terms of dy. So I need to take y equal x to the 2/7, and I need to solve for x. So x equals y to the 7/2. So that has to be y to the 7/2. In my inner curve, right minus left, my left curve is just 0 because it's this vertical line of 0 here. Now of course that would just be y to the 7/2 because when you subtract 0 you just get y to the 7/2, and I get a solution here of 2/9 as well. So I think on this one either way looks pretty easy, but since we're already solved for x, maybe the dx is a little more simple, a little more straightforward. So again, we're focusing on just setting these problems up. You can integrate and evaluate them, otherwise this lecture would be really long, longer than it already is. Okay, let's go ahead and find the region. And I guess the reason these end up being long is I want to make sure you have lots of examples to look at. If you understand them, you don't have to watch them. You can just scrub through them to the next example. But I want to make sure that you have a lot of information to go by. So let's look at region bound by y equal 10. And let's do another trig function. And y equal 10 sine of x. And let's do this on the interval from 0 to pi over 2. Yay, trig functions. Okay, so y equal 10 is a horizontal line. And then let's talk about trig functions. So it said 0 to pi over 2. So let's go pi over 2 clear out here. So if we plug a pi over 2 in here, sine of pi over 2 is 1. 1 times 10 is 10. That's going to touch right here. And at 0, it's going to touch right here. Now we know the sine curve. The sine of 0 is 0. So if we're just looking at a general sine curve. If we plug in a pi over 2, sine of pi over 2 is 1 times here. So we can see what's going to happen is this is the sine curve. But I'm only looking at this piece of the sine curve. So this would look similar to our last graph, but this is a trig function. So what I'm trying to figure out then, let's see here, get a good one. Here's my area that I'm trying to find. It's bound. I'm trying to figure out if I want to use horizontal or vertical. Well, when trig functions are involved, it's usually easier to go with keeping this in terms of x, because if I don't keep it in terms of x, I'm going to have to use inverse trig functions, and I really don't know much about integrating an inverse trig function right now. So I'm definitely going to go with my vertical rectangles in dx. So when I set this up, this would be the integral from 0 to pi over 2. My upper curve would be 10. And then of course this lower curve right here would be 10 sine of x dx. So I think that's the easiest way to set this one up. Now if you want to go ahead and integrate it, this equals 5 pi minus 10. And it's a good little problem to integrate, just because remembering your antiderivatives is going to be important. Okay. I just want to set a couple more up for you. If you have the hang of this, obviously you don't need to continue to watch the lecture, but I want to make sure you have lots of problems to go back and look at in case you get stuck on your homework. So let's look at two more. Region bound by, and let's look at y equal x minus 6 quantity squared and y equal 2x minus 12. Okay, so this is a line, positive slope. This is x squared. This is a parabola opening up. So I kind of already have an idea what this is going to look like. It'll probably look like something like this where I find that region. I want to find my points of intersection. And to find your points of intersection, you'd set these equal to each other. You'd FOIL on the left, x squared minus 12x plus 36, subtract everything across, set it equal to 0. Use your zero factor property after you factor. So I get x equal 6 and x equal 8 are my points of intersection. Okay, so here would be 6 and here would be 8. We'll kind of exaggerate this a little bit. So if we plug a 6 in here, we can see that 6 minus 6 is 0, so that would be this point right here. And if we plug an 8 in here, 8 minus 6 is 2, 2 squared is 4. Now it doesn't matter which one I plug them into, since they're my points of intersection, I'll get the same value back out. So I think the easiest one to do is to plot here that my slope is 2 and my y-intercept is negative 12, so you can see that these would have passed down there. Okay, and now I need to figure out if this curve is above or below. I'm pretty sure it's below, but we better check a point in here. So I want to check 7. So if I plug a 7 in here, 7 minus 6 is 1, 1 squared is 1. So it looks like to me it's underneath, but let's be sure. Let's plug 7 in over here. 7 times 2 is 14, minus 12 is 2, which would be up higher. So we were right. Whoops, totally missed that. Let's try that again. And we'll just move this point to match that. So you can see that this is set up perfectly for vertical rectangles. Okay, because everything's already solved for in terms of x, so I should just leave it like that. So let's go ahead and set up my integral. These vertical rectangles are going to travel from 6 to 8 to cover this area. They're going to start over here and go from 6 to 8. And then my upper curve would be the line. That would be the 2x minus 12. And then the lower curve would be the parabola, the second degree polynomial. Now, when you are working in my math lab, if you need to simplify and rewrite this, you would distribute the x minus 6 quantity squared, etc., and combine like terms before you try to integrate this. Okay, so make sure you simplify this first. And if you do go through the work of setting this up, this would equal 4/3 when you were done. And again, take the time to go through these, because on a test or a handwritten homework, the setup is going to be very, very important, but you'll actually have to find solutions there. I just don't want to spend the time during the lecture to do that, otherwise this would be like a 3-hour lecture. Okay, let's go ahead and look at one more. This one's just a little bit different. It's a little harder because instead of y equal, we have x equal. So let's go ahead and find the region bounded by, let's do x equal y times y minus 18 and x equal negative y times y minus 18. So right away, when I'm looking at this, everything is in terms of y already, so I think dy is easier here. So I'm going to want horizontal rectangles. Okay, so I'm going to leave these, distribute y squared minus 18y. This would be a negative y squared plus 18y. So y squared minus 18y, that's a parabola opening on its side to the right. This is a parabola opening on its side to the left. So my thought is this is going to look something like that. So let's go ahead and curve sketch it and find the points of intersection. So points of intersection. So set them equal to each other. Y squared minus 18y equals negative y squared plus 18y. Adding across, I have 2y squared minus 36y equals 0. Factor out a 2y and left with y minus 18. So I get y equals 0, y equal 18. So when I start to curve sketch this, since my y values are 0 and 18, I think for the most part I'm going to be probably in quadrants 1 and 2. So I'm crossing at 0 and I'm crossing up here at 18. Okay, so if this is our general picture that we already know about, I could plot some points to figure out what's going on here, or I could just kind of try and sketch it in. Now I'm not positive how far these go out. That would be easy enough to figure out. I could go ahead and choose some x values and figure out where those points are, but the most important thing is I figure out what my right curve is. And notice the right curve is always on the right. I don't have to switch. I don't have two regions here, and the left curve is always on the left. So I'm using horizontal rectangles, so I definitely have my dy's going here. Whoops, this one needs to go out further. So when I set up my integral, I'm going to integrate from 0 to 18 of my right curve, and my right curve was this x equal y squared minus 18y. So this is going to be y squared minus 18y for my right. And then the left curve was this negative y squared plus 18y. And again, it's very, very important that you have your parentheses set up correctly, because if you don't have your parentheses set up correctly, what ends up happening then is you have your, I think I have these backward. Let me fix this up. This curve that opens to the left should be my negative y squared, so I have this written wrong right here. I had my little sketches up here correct, I just forgot to follow their examples. So this was the x equal negative y squared plus 18y. And then my left curve was this x equal y squared minus 18y. Again, plot a few points and those will become a lot more clear. So we're going to integrate from 0 to 18. Now get my correct right curve in here. And I have negative y squared plus 18y for my right. And my left is y squared minus 18y. I need to make sure I subtract the entire quantity. And so when I simplify this, this is going to be the integral from 0 to 18. Negative y squared is negative 2y squared. 18y, distribute the negative plus 18y is plus 36y dy. And again, don't forget the dy's. Now if you want to integrate this and evaluate this, you absolutely can. Get 1,944 for your solution. But again, we want to focus on setting these up. On handwritten homeworks in My Math Lab and on your exams, you'll actually be setting up and evaluating them. As usual, good luck. If you have questions, let me know. You can set up a time for us to meet online if you're interested. If you're nearby, you can also stop by my office. Meeting online works pretty well. Also taking screenshots of any of your questions along with your work is very helpful too. Good luck. I hope you enjoy working with the trig functions as much as I do.